BSc Chemistry Terpenes presented by Dr. Giridhar M, Assistant Professor of Chemistry, Department of Collegiate Education. Contents: Introduction to terpenes and terpenoids, properties of terpenes and terpenoids, isoprene rule, classification of terpenes and terpenoids. Let us start with introduction. Terpenes and terpenoids constitute large class of natural products built from isoprene units. Terpenes are technically only hydrocarbons while terpenoids are oxygenated. So ಇಲ್ಲಿ terpenoids, they are natural products, so built from one or more isoprene units, and ಈ isoprene units, they are made up of hydrocarbons. So that means hydrocarbons are made up of carbon and hydrogen only, whereas terpenoids, they are oxygenated. So that means they contain carbon, hydrogen and oxygen. Terpene and terpenoids are produced by variety of plants, particularly coniferous plants. So especially bark, flowers and leaves of these coniferous plants contains terpenes, and some insects also produce terpenes. So these terpenes have very strong odor, and these are produced by plants to deter herbivorous animals. So that ಅಂದರೆ ಸೊ ಇಲ್ಲಿ ಹಸು ಆಗಲಿ ಕುರಿ ಮೇಕೆ ಈ ಥರದವು ಆ ಗಿಡಗಳನ್ನ ತಿನ್ನಬಾರ್ದು ಅಂಥೇಳಿ ಅವು ಒಂದು ಸ್ಟ್ರಾಂಗ್ ಓಡರ್ನ ಪ್ರೊಡ್ಯೂಸ್ ಮಾಡ್ತವೆ. ಸೊ ಜಸ್ಟ್ ಟು ಡಿಟರ್ ದೋಸ್ herbivorous animals. So those are terpenes. Terpenes are coniferous plants. That means their leaves are having cone-like structure. So it can be seen in image. Terpene are also major biosynthetic building blocks. So for example, steroids are derived from triterpene squalene. Similarly, vitamin A is composed of terpene units called isoprene. So examples for terpene include myrcene, farnesol, menthol, citrol, camphor, so etc. So these are the examples for terpenes. Next, general properties of terpenoids. Most of terpenoids are colorless, fragrant liquids, and they are lighter than water. So density, since they are oils, they are lighter than water, and they float on water. So volatile with steam, and very few of them are solids. So example, camphor is a solid, and all these terpenes are water insoluble, and they are soluble in organic solvents because they are non-polar compounds, and most of them are optically active. That means they can rotate plane polarized light. Next property, they are open chain or cyclic unsaturated compound. So terpenes can be open chain or they can be cyclic, and they are all unsaturated compounds. They have one or more double bonds. So they show the properties of this double bond, that is they undergo addition reaction like hydrogenation, halogen, etc. And a number of addition products have antiseptic property. Similarly, they also show polymerization and dehydrogenation property. They are easily oxidized nearly by all oxidizing agents. Oxidizing agent like KMNO4, bromine, okay, K2Cr2O7, osmium tetroxide, all these oxidizing agent oxidize terpenes easily. And on thermal decomposition, most terpenoids yield isoprene as one of the product. So these are the properties of terpenoids. Isoprene rule. Let us move to isoprene rule. Isoprene rule states that terpenoid molecules are constituted from two or more isoprene unit, And basically this isoprene unit having formula C5H8N. Okay, so isoprene unit it's having formula C5H8. so N is terpenide may contain 2 or more these isoprene units, and N gives the number of isoprene unit which is present in that terpenide. Further, Ingold suggests that isoprene units are joined in terpenide via head to tail fashion. So if we see isoprene unit, this part is head and this part is tail. So this is head part and this is tail part. So special isoprene rule states that terpenide molecules are constructed of 2 or more isoprene units joined in head to tail fashion. So both Ingold and isoprene rule tells that isoprene are joined together in terpenide by head to tail fashion. However, Ingold and special isoprene rule can only be used as guiding principle and not as fixed rule. So why is this? This is because some terpenes like carotenoids, they are joined by tail to tail fashion. Okay, that means it is not necessary that all terpenoids should contain head to tail fashion, but some of the terpenoids can also have tail to tail fashion, and hence these rules are not fixed. Okay, these rules are not fixed. So next, in applying isoprene rule, we look only for skeletal unit of carbon. The carbon skeletons of open chain monoterpenide and sesquiterpenoids are, so this is monoterpenide myrcene. So here double bonds are there, but we do not consider this double bond. We only take the skeletal structure of this terpenoid, that is myrcene, and we see that here 2 isoprene units are there. This is head, this is one isoprene unit and this is another isoprene unit, and they are joined together by head to tail fashion. And similarly farnesol, this is also a sesquiterpenoid. So here CH2OH is there. So we do not consider all these things, we only consider the skeletal structure, and we see that in this case 3 terpenoid units are present and they are connected by head to tail fashion. So this is a head and this is a tail, and this is a tail of another terpenoid, and this is the head, and once again this is the tail and this is the head of third terpenoid. Ingold pointed that gum alkyl group affects the stability of terpenide. Summarize these results in the form of rule called gum dialkyl rule, which mostly stated as gum dialkyl group tend to render the cyclohexane ring unstable when attached to cyclohexane, and it stabilizes 3-4-5 membered ring. So that means if you see these are the 2 alkyl groups. When these 2 alkyl groups are attached to same carbon atom, then this is called gum dialkyl group. So in this case 2 methyl groups are attached to same carbon, hence it is called as gum dimethyl group. So when this gum dimethyl group is attached to 6-membered ring, the ring becomes unstable. That means it can easily break to give this form. Okay, and when this gum dialkyl group is attached to 3-membered, 4-membered, 5-membered ring, the ring gets stabilized. The ring is stabilized. So that is about stability of the ring, which is explained by dialkyl. Okay, gum dialkyl rule. Next rule is about closing of the ring. This rule limits the number of possible structure in closing the open chain to ring structure. Thus, the monoterpenide open chain give rise to only one possibility for monocyclic monoterpenide. So that means in case of monocyclic, that means terpenoids containing only one ring, monoterpenes, that means 2 isoprene units, the ring closure, when ring closure takes place, So it will give only one product. Okay, it will only give one product. So in this case, para-cymene, when ring closure takes place, it gives a 6-membered ring. Okay, so this is just one product. Next, bicyclic monoterpenoid containing 6-membered and 3-membered ring. When thus ring closure of 10 carbon open chain monoterpenoid gives 3 possible bicyclic structure. So that means in case of bicyclic compounds containing 6-membered and 3-membered ring, when ring closure takes place, it can give 3 isomers. Okay, 3 isomers. That is, one is camphor 6+5 system, another one is pinene 6+4 system, and carene 6+3 system. So if we count from here, this is bridged carbon 1, 2, 3, 4, 5, 6. Okay, so this is 6-membered ring, and from here 1, 2, 3, 4, 5. So this is a 5-membered ring. So this is 6+5 system, and pinene. So this is 6-membered ring. Okay, and then this is 4-membered ring, 6+4 system, and this is 6-membered ring and 3-membered ring, 6+3 system. So that means in case of monoterpenoids with monocyclic, okay, monocyclic terpenoid, it will give only one product on ring closure, whereas in case of bicyclic compound on ring closure, it gives 3 different product. So next we will move to classification of terpenoid. So most natural terpenoid hydrocarbons have the general formula C5H8N. They can be classified on the basis of value of N, that or the number of carbon atoms present in the structure. So here we can see, whenever value of N is 2, it is called as monoterpenoid. That means 2 isoprene units are there in this, and total 10 carbon atom. When value of N is 3, that is when it contains 3 isoprene units, it is called as sesquiterpenoid, and the number of carbon atoms present is 15. And whenever 4 isoprene units are present, so it has 20 carbon, and it is called diterpenoids. When 5 isoprene units are present, 25 carbon atoms will be present, and it is called sesquiterpenoid. When 6 carbon atoms are present, a total of 30 carbon atoms will be present, and it is called troterpenoid. And when 8 isoprene units are there, 40 carbons are possible in that molecule, and it is called tetraterpenoid. And when 9, okay, so this is 9, when 9 isoprene units will be there, so 45 carbons will be there, and it is called as polyterpenoids. And further, each of these can be subdivided into subclasses according to number of ring present in the structure. So that means monoterpenoid can be further classified as acyclic terpenoid. Acyclic terpenoid does not contain any, it contains only open structure, it does not contain any ring. Monocyclic terpenoid, it contains only one ring in the structure. Bicyclic terpenoid, it contains 2 rings in the structure. Tricyclic terpenoid, it contains 3 rings in the structure. Tetracyclic terpenoid, it contains 4 rings in the structure. So example for monoterpenoid. So as I already told, monoterpenoid can be further classified as acyclic monoterpenoid. So example for this is myrcene, citrol, geraniol. Okay, 2 isoprene units will be there. That is, in monoterpenoids 2 isoprene units, and this is acyclic monoterpenoid. So there will be no cyclic ring structure. And next one is monocyclic monoterpenoid. Mono means one ring will be there here. So 2 isoprene unit with 1 ring. So example is limonene, alpha terpenol, menthol. So limonene is the one compound which is found in the lemon peel. And the ಕಿತ್ಲೆ ಹಣ್ಣಿನ ಸಿಪ್ಪೆಯಲ್ಲಿ ಇರ್ತಕ್ಕಂಥ ರಸ ಏನಿದೆಯಲ್ಲ, that is limonene. Okay, limonone. Similarly, third one is bicyclic monoterpenoid. Bicyclic andre here it contains two rings, and monoterpenoid means two isoprene units. So this is thujane, which is 6 plus 3 membered ring, pinane 6 plus 4 membered ring, camphor 6 plus 5 membered ring. Next is B, sesquiterpenoids. So this is sesquiterpenoid can be further classified as acyclic sesquiterpenoid. This is sesquiterpenoid, monocyclic sesquiterpenoid, bicyclic sesquiterpenoid. So for acyclic sesquiterpenoid, example is farnesol. Sesquiterpenoid means n value is 3 and 3 isoprene units will be present. So this is 1, okay, 2 and then 3. Similarly, for monocyclic sesquiterpenoid, zinziberne is another example, and for bicyclic sesquiterpenoid, cadenine is an example. So in this case, two rings will be there. In case of monoterpenoid, single ring will be there. Monocyclic monoterpenoid, single ring. So C is diterpenoid. Diterpenoid means here 4, n value is 4, that is 4 isoprene units will be there. For acyclic diterpenoid, example is phytol. And for monocyclic diterpenoid, so example is retinol, that is vitamin A, that is in this case one ring will be present. So this is about classification of terpenoids. So reference. Thank you.